Hey, Wade Hampton Chemistry. Today we're going to be talking about the difference between the Bohr model of the atom and a newer, although still quite old, model of the atom known as the wave mechanical model of the atom, or the quantum mechanics model of the atom. And we're also going to be getting into something called electron configuration today. The Bohr model of the atom had a couple of main ideas. The nucleus was made of protons, and the nucleus was made of neutrons, and electrons were going outside that nucleus in these circular orbits, kind of like the moon orbits the Earth, or planets orbit a star. The wave mechanical model of the atom is a little bit different. And the biggest difference is the difference between orbits and orbitals. So an orbit is just a circular path. And an orbital, on the other hand, is a 90% probability map. Okay, so it's a probability map. So basically, this guy named Schrodinger came up with the idea that electrons are not just restricted to classical physics in terms of, hey, an object is going to move in a straight line, kind of physics. He said that, as matter gets smaller and smaller and smaller, that matter tends to move more like a wave. And so, you can imagine, hey, if I've got my nucleus here, the electron may be going around the nucleus, but it's not just going around the nucleus, it's going around the nucleus in a wave. And as he did that, this helped to explain why orbits in the Bohr model, or if you want to relate it to orbits in the Bohr model, why electrons could only occupy certain distances from the nucleus. Because if you had, say, an orbit out here or a wave out here that didn't line up, then that would be a average distance from the nucleus that would not be allowed because of the destructive interference of the waves. And so, there were only orbits that could be in certain distances from the nucleus. You also got into the idea that, hey, if you got more than one electron, then you can get into some scenarios where those electron repulsions and the wave-like motions can basically just create too many variables for you to know the path that the electron is taking and where it's going to be at any given time. You can't know the velocity and the position of an electron at any given time. This is something called the Heisenberg uncertainty principle. Another way to think about it would be kind of like this, saying, if here's my nucleus and, you take a snapshot in time of where the electron is, okay, maybe it's here, maybe it's here, maybe it's here, maybe it's there, you do it again, and you keep taking pictures of where the electron is around the nucleus of the atom. And, sometimes it's here, sometimes it's there, sometimes it's way up here. Then, if you used a 100% probability map, technically the electron could be anywhere. So you have to use something less than 100% to actually get a shape and a size for the area that the electron could be in. And so, they said, all right, it's in here 90% of the time. We're going to call that area just an area where, the electron can be found, an orbital, that 90% probability map. Now, any orbital can hold up to 2 electrons, according to Schrodinger. Now, if you start looking at more complicated atoms than, say, just hydrogen and helium that have the 1 energy level, you start getting some interesting shapes to orbitals due to the destructive interference and repulsion of electrons that are moving in waves. And so there's a really good video that kind of shows how these orbitals nest on each other that I'm totally going to steal just for the purposes of this presentation. It's pretty short here. Really quickly, and we're just going to roll over to a short YouTube video that I'm going to kind of narrate over here. So this is showing orbitals stacking into a scandium atom. And what I want you to realize is that each of these 3-dimensional shapes, this is the nucleus, that's coming in here, is basically just an area, an orbital. It's a 90% probability map that can hold 2 electrons. Now, these orbitals come in different shapes. The round ones are S shapes. If I back this up here just a little bit, you can see that the 1s orbital is the same shape as the 2s, but the 2s orbital is just in a higher energy level, a little bit farther away from the nucleus. So we use these letters to designate shapes. Now here we've got a new shape. We call this dumbbell-shaped orbital a p orbital. So this is still part of the second energy level, but there's p orbitals. Whenever p orbitals show up, they always show up in sets of 3. You see, them stacking in on the x, y, and z axes at 90-degree angles to each other. Once those are filled, the second energy level is full, and you start moving to the third energy level, and a pattern repeats in that you see an s orbital again. You also see p orbitals in the third energy level. And you can put 2 more electrons in every single one of these shapes that's stacking into this three-dimensional configuration here. Once you get to the end of the 3p orbitals, then you'll go to the fourth energy level, and you'll see the S shape repeated. And then something really weird happens. You go back into the third energy level, and you get a new shape. This is the new shape that appears in the third energy level. This is kind of the black sheep d orbital. Most d orbitals have this kind of four-leaf clover-looking shape, or like 4 balloons tied together in the middle. And there's 5 of these things that will stack in here in different orientations, just facing different directions. Okay, and you can see this model is already getting very complicated. Okay, so don't worry about trying to think if you would have to draw these things in 3 dimensions, but I want you to hopefully understand by the end of this lesson how to model where the electrons are in each of these different shaped orbitals in different energy levels around an atom. Okay, all right, so let's go back to our lesson here. All right, so within each energy level, there can be 1 or more orbitals. And basically, as you go up in energy level, you're going to get more different kinds. Like this is S shape. These are the P shapes, the D shapes, and the F shapes. If you look at the first energy level, the first energy level is going to just have an S. The second energy level is going to have an S and a P shape. The third energy level is going to have an S and a P and a D shape for the different kinds of orbitals that can appear. So the idea is every time you jump up in energy level, you're going to get a new shape of orbital that's going to start to pop in there. Okay. Now every energy level is a little bit farther away from the nucleus, and you could see that in that video. The same shapes were repeated. They just were a little bit larger and a little bit farther away from the center for the size of those probability maps. Okay. Now, atoms tend to arrange themselves in the most stable way possible around a nucleus. And we call where those electrons are an electron configuration. Okay, now there's 3 rules that explain electron configurations. The Aufbau principle, the Pauli exclusion principle, and Hund's rule. Okay, we're going to look at each of these rules individually, and then we'll put it all together at the end here. Okay? Now, the Aufbau principle basically is the order that you would fill in electrons into an atom. And it says that electrons enter orbitals of lowest energy first. This is similar to the Bohr model. When we were making Bohr models, we said that electrons have to go in that first energy level that's closest to the nucleus first. But this is a little bit more complicated because you can have multiple orbitals of different shapes within each energy level. So we've got to organize those a little bit. Here's an energy diagram, and it's important to understand that inside an energy level, the S is always the lowest energy level shape of orbital that's within each energy level. So you notice the S is a little bit lower, the 2s is lower than the 2p's, 3s is lower than the 3p's, the 4s is lower than the 4p's, so the S is the lowest energy kind or shape of orbital within each principal energy level. If you wanted to know the order that you would have to fill in those shapes, you could just go up this energy level diagram. Now, each of these boxes is representing one of those orbitals, and each of these arrows represents an electron inside that orbital. So each orbital can hold 2 electrons there. But you have to fill it this way. You can't fill in the 3p before you fill in the 2s or the 2p because it's higher in energy. The Pauli exclusion principle says that every orbital can hold at most 2 electrons. And a sublevel is a set of orbitals. Okay, now some orbitals, like an s orbital, sublevel may only have 1 orbital in it. P's tend to come in sets of 3, D's 5. Let's go ahead and lay that out here. All right, so an s sublevel has only 1 orbital. So s's only show up as one shape at a time. But every orbital can hold 2 electrons. So one orbital can hold 2 electrons. When p orbitals show up, you might remember from the video that those things came in a set of 3 orbitals per energy level that oriented themselves at right angles to each other, and every single one of those could hold 2 electrons. So 3 times 2 would mean the whole p sublevel, or all 3 p orbitals, could hold a maximum of 6 electrons. A d sublevel has 5 orbitals in a set of orbitals that would constitute a sublevel, and if each holds 2, that would hold up to 10 electrons. An f sublevel has up to 7 orbitals, and 7 times 2 would mean that an entire f sublevel holds up to 14 electrons. Now, every box in a orbital diagram is going to mean an orbital. We're not drawing these 3-dimensional shapes. We're doing this a little bit more simply. And if you want to put electrons in that orbital in an orbital diagram, then you can just put arrows into that orbital diagram. Something like this. Now, physics says that if you're going to cram 2 electrons in a small space together, they're going to minimize their repulsion by spinning in opposite directions. So when the arrows are meant to show that the electrons would be spinning in opposite directions to minimize their electrical repulsion. All right, 2 down. We've talked about off-ball. We've talked about Pauli. The last rule that governs electron configurations is something called Hund's rule. Now, Hund's rule says that when electrons occupy orbitals of equal energy, 1 electron enters each orbital until they all contain 1 electron with parallel spins. All right, let's focus in on this. Orbitals of equal energy. Let's go back to this diagram here just for a second. When are you going to have orbitals of equal energy? Well, all 3 of these have equal energy. All 3 of these have equal energy. All 5 of these have equal energy. Okay, basically orbitals of the same type in the same energy level. So we're talking about similar orbitals within a sublevel. Now that's not really going to be a big deal if you're talking about s sublevels because there's only 1 orbital per sublevel. But if you're talking about p or d or even f sublevels where you have more than 1 orbital, more than 1 box, then this is going to be a rule that's going to apply. Okay, so let's take a look at an example where Hund's rule would apply. Let's talk about oxygen. Okay, so oxygen is an element that has 8 electrons in it. And if you were to start filling in an orbital diagram for oxygen, you would start off with the 1s, the first energy level in an S-shaped orbital. Now, S sublevels only come in a set of 1 orbital, so you'd only draw 1 box for that. Okay, this would be room for the first 2 electrons. I'm going to draw an up arrow and a down arrow for the first 2 electrons. The 2s orbital, again, this is in the second energy level, but it's the same type of orbital and same type of sublevels. So there's only 1 box, only 1 orbital per sublevel here. So this would just be 1 box that held another 2 electrons. If you look at the order of filling according to the off-ball principle, what comes after 2s? Well, 2p. All right, so this is when Hund's rule is going to start to apply here, because now we have 3 different orbitals in a 2p sublevel that are all the same kind of orbital in the same energy level. These are orbitals of equal energy. And orbitals of equal energy are going to have 1 electron entering each orbital until they all have 1, with parallel spins. So what this means is that electron 5 would go here, electron 6 would go here in the same direction, electron 7 would go here, and then electron 8 would go here. Okay? So this is just an introduction into electron configuration and orbital diagrams. Hope this helps. Until next time.